This video will be to get some practice on computing the inverses of matrices using elementary operations, elementary transformations. And we will do so by doing some problems from NCERT Class 12 Exercise 3.4. And let's begin. So let's take problem number 2. So problem number 2 has a matrix of 2, 1, 1, 1. And you have to compute its inverse. So the general strategy of computing inverses using elementary transformations is the following. So if you have any matrix A of which you want to compute the inverse, you can always write it as I times A, and that's just general. It's like writing x equals 1 times x. And given that you can write it as that, you can perform operations, you can perform row or column operations to get this to a form of the identity matrix. And you have to perform the same operations to, let's say, get some matrix B. So it's legitimate to do so since you're doing the same things to both sides. It's like solving a linear equation. And so in this case, you would get I to be equal to some matrix B times the matrix A. So that just means that the matrix B is the inverse of the matrix A. So let's try this strategy out using this matrix. So you have 2, 1, 1, 1, and that will be equal to I for this 2 by 2 order. It's 1, 0, 0, 1 times the matrix A. So the goal would be to reduce it to do some manipulation to get it into the identity matrix. Get it to the identity matrix, and we will perform the same operations in here. So let's see. So let's try subtracting. Let's try subtracting R2 minus R2 from R1. Why do I do that? And that's what took me some time to think about it. It's because if you do that, if you see carefully, if you subtract row 2 out of row 1, then row 2 will remain the same. It will just remain 1, 1. And in row 1, you will have 2 minus 1 and 1 minus 1. And if you compute that, 2 minus 1 is just 1, and 1 minus 1 is 0. So you have the first row of the identity matrix, and that's something that we hope for. If you do the similar operation, if you do the same operations on the second matrix that you have, R1 minus R2, so again, row 1 is going to be the same, row 2 is going to be the same, and row 1 will convert to 1 minus 0 and 0 minus 1. And so 1 minus 0 is just 1, and 0 minus 1 is negative 1. And that times the matrix A, that will just stay there. Now you have to continue doing some manipulation to convert this row into the second row of the I 2 by 2 matrix, which is 0, 1. And if you look closely, then doing the following operation, writing row 2 as row 2 minus row 1, if you do that, so row 1 now in this matrix is going to be the same. Row 2 will now become row 2 minus row 1, so 1 minus 1 and 1 minus 0. So 1 minus 1 is just 0, and 1 minus 0 is 1. And you do the same operation on the second matrix that you have here. So let me just write that in color because that will be the answer. This already is the identity matrix, so whatever comes here would be the answer to this problem. If you do this, so row 1 is going to stay the same because you're performing operations on row 2. So for row 1, you just write negative 1 out. In row 2, you have to write row 2 minus row 1. So 0 minus 1 and 1 minus negative 1. And all of that times A. If you finally compute that, so 0 minus 1 is negative 1, and 1 minus negative 1 is 1 plus 1, and that's equal to 2. So this matrix right here, 1, negative 1, negative 1, 2, is the inverse of the matrix that we started with, 2, 1, 1, 1. And so you can do the same. You can do the same for all the 2 by 2 matrices that you have. You can perform some applications to somehow get it to the form of a 2 by 2 identity matrix. And once you're able to do that, whatever answer you get on the right hand side is actually the inverse of the matrix. So you can do the same for all the 2 by 2 matrices that you have. Let's try an interesting problem that's in the exercise. That's problem number 12. So you have the matrix 6 minus 3 and negative 2 1. So 6 negative 3, 6 negative 3, and negative 2 1. Now in matrices like this, and in all matrices in general, just observe whether you have some nice multiple, whether one row is a nice multiple of the other. So in this case, you can clearly observe that row 1 is just equal to negative 3 times row 2. So negative 2 times negative 3 gives you 6, 1 times negative 3 gives you negative 3, and thus if you perform the operation R1 plus 3R2, that's just equal to the zero row. So if you perform that operation, if you, let's just write it in the form that we have to. So A equals I times A, I times A. Now if you perform the row operation, R2 going to R1 plus 3R2, if you perform that operation right there, then you have 6 negative 3. R1 still remains the same. However, in the case of R2, you get all zeros, since we just saw that. And you could do the same thing for this matrix, and you could have got some matrix right there, and it doesn't matter. It doesn't matter even if you don't get the answer. By the way, the answer for that part would be 1 0 3 1. But even if you get this matrix, it doesn't matter, since having a single row to be all zeros means that the inverse doesn't exist. Inverse doesn't exist. And while we are at this, and I also talked about this in the video on computing matrix inverses, you can also try to check beforehand by computing the determinant of this matrix. And determinant is a concept that we'll develop. But for now, just for 2 by 2 matrices, that would be doing the cross multiplication of its entries. So 6 times 1 minus negative 2 times negative 3. And if you do that, it's 6 minus 6, and that's equal to 0. So for any matrix whose determinant is 0, the inverse will not exist. So we have talked about 2 by 2 matrices, one whose inverse exists and one for which it doesn't. Let's do a 3 by 3 matrix, and that would at least call for a nice practice. So the matrix is 2 0 negative 1 5 1 0 0 1 3. So 2 0 2 0 negative 1 5 1 0, I guess, yeah, 5 1 0 0 1 3 5 1 0 0 0 1 3. And again, you will write the identity matrix, but in this case, the identity matrix will be of order 3 by 3. So 1 0 0 0 1 0 0 0 1, and that times, let me do that in brown, that times the matrix A. Now again, you have to do the same types of operations that you did. So let's try some things. So if you see carefully, then you have to convert convert this matrix, you have to convert this row into 1 0 0, this to be 0 1 0, and this to be 0 0 1. So let's try the first operation. So let's do R1 goes to 3 times R1 minus R2. And if you do that, if you do that, so R1, instead of R1, you are going to write 2 times 3 times 2 minus R2 is 5, then again 3 times 0 minus 1, and then 3 times -1 minus 0, and all of the rows stay the same. 5 1 0, and then 0 1 3 here. Now you have to do the same thing on the other side, otherwise this operation just doesn't make any sense. So you have to do 3 times 1 minus 0, 3 times 0 minus 1, and then 3 times 0 minus 0, and then all other rows are just written as they are. If you compute these, if you come out by computing these, so 3 times 2 minus 5 is 1, 3 times 0 minus 1 is -1, 3 times -1 minus 0 is -3, And on this side, of course, there is an a right there. On this side, you have 3 times 1 minus 0 is 3. It's equal to 3. 3 times 0 minus 1 is -1. And 3 times 0 minus 0 is just 0. It's just 0. So -1 here and 0 there. Now we can continue doing that. We can continue extending this. So we have to make this to be 0, make this to be equal to 0. So what if we do the following? We take row 2 and convert it into the difference of row 2 minus 5 times row 1. And what happens by that? So 1 -1, let me write that in different color. So 1 -1 -3, that remains the same. Instead of row 2, now you write 5 minus 5 times 1. And then here you write in the second entry here 1 minus 5 times -1. And here you write 0 minus 5 times -3. And the third row remains the same. And that is equal to, you do the same operations, same sets of operation on this matrix, on the matrix that you have right here. So the first and the third row remain the same, they are not changed. And here in the second row, you do row 2, 0 minus 5 times 3, 1 minus 5 times -1, and 0 minus 5 times 0. And so you compute them. You compute these numbers that you have found out. So instead of 5 minus 5 times 1, you write 0. That's what you were supposed to get. 1 minus 5 times -1 is 1 minus -5. That's just 6. And here 0 minus 5 times -3 is negative of -15, and that's just 15. Okay. And here on the second matrix, you have 0 minus 5 times 3, so -15. And 1 minus 5 times -1 is it's 1 plus 5, and that's 6. And in the third entry here, you have 0 minus 5 times 0, that's 0. And so that's it for this operation that you did. So far so good. Now let's try some more stuff. Let's try I don't know. So we have to take these to be 0, to be equal to 0, and you see here that if you add row 3 to row 1, you add row 3 to row 1, then you can get these to be equal to 0. You can get those two entries to be equal to 0. So let's take row 1 and convert it into row 3 plus row 1. So let me write the braces again. So again, right there, and times A. So in the place of row 1, firstly you are doing, let's just write it as row 1 plus row 3, just for nice convention. So 1 plus 0, and then -1 plus 1, and then -3 plus 3. You are just adding up these two rows, row 1, row 2, row 3, and you're adding just R1 and R3. Then you just write all other rows as they are. You don't do anything with them. And again, so in this case, in the case of the second matrix right here, you are doing the same. So you're adding 3 plus 0, -1 plus 0, and 0 plus 1. And then for the second, third, and the third row, you're just leaving them as they are. You don't do anything to them. And if you do that, if you compute these matrices, if you compute the entries that they are, so 1 plus 0 is just 1. -1 plus 1 is 0. That was the intent that we had. And -3 plus 3 is 0. So we have solved the first row. You have got the first row. That's something that you should cheer about. And 3 plus 0 is, well, 3. -1 plus 0 is -1. 0 plus 1 is 1. Great. So now we have solved for the first row. Let's move on to the other rows that you have. So now let's think. Let's put on our thinking caps and let's think. You have to take this and you have to take this to be 0. So there it is 15, and in row 3 there is a 3. So 15 minus 5 times 3 equals 0. So what that means, if 15 comes from row 2 and you subtract from it 5 times row 3, that's where 3 comes from, it would give you 0 in this entry, and that's exactly what we want to do. So let's do that. So let's write R2 to be R2 minus 5 times R3. And again, so the first row remains the same. You don't have to worry about the first row in this case. It will be just 1, 0, 0. We are not going to touch it. And R2, for R2, you are going to write 0 minus 5 times 0, then 6 minus 5 times 1, and 15 minus 5 times 3. And then you write the third row as it was. And on the other side, on the right hand side, you again do the same operations. So the first row remains untouched. You don't do anything about that. And minus 15 minus -15 minus 5 times 0, 6 minus 5 times 0, and then 0 minus 5 times 1. Sorry, I'll just erase the braces a bit. And the third row just remains the same. You don't have to worry about the third row in this case. Great. So what that means is you are now left with, if you compute the matrix that you have here, you have 0 minus 5 times 0. 0 minus 5 times 0 is just 0. And then 6 minus 5 times 1. That's a bit lucky. You get 1 here. So you get 1 here. And then you have 15 minus 5 times 3. So 15 minus 15. That's what is the intent, and that's equal to 0. Here in the matrix on the right hand side, you have -15 minus 5 times 0. So it still remains -15. 6 minus 5 times 0 remains 6. And 0 minus 5 times 1 is -5. Great. Now you have, luckily, you have also solved for the second row. We were hoping to eliminate the 15, and we have sort of got the entire row as a gift. So, at last, you have to somehow manipulate the third row. Now if you see, you have to convert this into 0 and this into 1. So let's do it one step at a time. So if you see, if you write the transformation R3 going to R3 minus R2, if you do that, what happens is you essentially get rid of this one right here. So if you write those matrices, so row 1 and row 2 remain the same, and here you have 0 minus 0, 1 minus 1, and 3 minus 0, and that would be equal to, on this hand you have, well, A still remains there, and you write the first and the second row as they are, so you just write them out, and now you have R3 minus R2 here as well, so 0 minus negative 15, 0 minus 6, and 1 minus negative 5. If you compute these, so 0 minus 0 gives you 0, 1 minus 1 gives you 0 again, that was the intent, and 3 minus 0 gives you 3. 0 minus negative 15 gives you 15, 0 minus 6 gives you negative 6, and 1 minus negative 5 gives you 1 plus 5, and that's equal to 6. And at last you want to convert this into 1. And there are no other entries, so what you can do is a very simple transformation. You can take R3 and you can divide it by 3 in this case. So R3 is, you will convert it into 1 over 3 times R3. You're dividing the entire row by the number 3. So you write the first and second row untouched. And so 0 by 3, 0 by 3, and 3 by 3, and that's equal to, you again write the first and the second row untouched, you don't do anything to them, and here you write 15 over 3, negative 6 over 3, and 6 over 3 all times A. And finally you solve this. So 0 over 3 gives you 0, 0 over 3 again gives you 0, 3 over 3 gives you 1, and yay, we have the identity matrix here of the order 3 by 3. And the answer here you would get, so 15 over 3 gives you 5, negative 6 over 3 gives you negative 2, and 6 over 3 gives you 2. So now you have I3 cross 3, and you have some matrix. You have this matrix right here. This matrix times the matrix, the original matrix A that we had, gives you the identity matrix. So what that means is this is the inverse of A, and that was a long problem to solve. See you in the next video.